This week we will talk about non-parametric methods. So let's start with histogram estimation. In parametric methods that we saw last week, including mixture models, we are talking about getting probability densities which are defined in advance. Typically, we will say that some data is following, for example, a multivariate normal distribution with some mu and sigma parameterization. And as such, a problem is to search for the right parameterization to use for these densities according to the dataset that we have at hand, for example. With non-parametric methods, we are looking to estimate the probability directly from the data. So the idea is to say we don't have parameters, we in fact use the data as the parameterization of our model. So with such approach, there's usually no hypothesis a priori, so we don't have any kind of assumptions on the distribution of data, more or less. And there are several approaches for that. For example, we have histogram estimation that are really simple approach that are relatively intuitive, given that we are making use of that since a long time. You used that before. There are some, I would say, more sophisticated approach that are related to histogram estimation that are kernel density estimations. So these are based on the use of a kernel to estimate the density from the data we have at hand. And we also have the k-nearest neighbors approaches. These approaches are using, in fact, the distance, some kind of distance or some kind of neighborhood measurement to define how we will process data, or we will make some estimation of the densities or estimating the right label for classification. So probability here, like if we say probability that x is less than a here, this is what we are dealing with this. It consists to evaluate the integration of the density px from minus infinity up to a. So we are looking what is the probability that the x is in between minus infinity and a, given the density function px that we have here, the likelihood px that we have. And as such, a way to make some estimation of that can be done through sampling. So let's assume that we have a data set in one dimension here for the example of n points. So we have the xt, so we have x1, x2, x3 up to xn. So this is the set of functions of points xt from 1 to n. And from that, we are able to estimate the probability that x is less than a in our domain simply by counting the number of xt that effectively have a value less than a. And the ratio of that over, so we are dividing this by n, so it's just looking at how many xt we have with value less of a versus the size of our sample set. So if we are looking to estimate, in fact, the value of x in a range from a to a plus h, this is a range. So the estimation of the probability that the x, whatever the x, is coming from that range is simply to look at the number of xt that are less than a plus h minus the number of xt that are less than a. So we are looking at, said otherwise, we can see we have a domain here, and so we are looking at a plus h. So we are counting how many samples we have here, and then we have a here, so we are counting the number of samples we have there, and so making this one minus this one give us the number of samples we will get in the interval. So this is a way to estimate the probability of getting a sample in that range, given the sample set that we have at hand. So we can approximate then the density. We can say, okay, our continuous density here can be estimated by a constant value. We could say, okay, we know maybe in practice that we have something that is like this too. Well, to be right, we should not go something like this. It looks like more or less a Gaussian, but let's assume that we don't really know what is the real distribution here. We can assume, so this is the Px. We can say that, okay, we will estimate in that interval. We know here that the real Px is varying, but we will just say, okay, let's use a flat estimation, a constant. We'll just say, okay, in that interval, the value is fixed. So this is an approximation, but assuming that the interval here is not that large, that approximation is relatively accurate, given that it is not that, the range is not too big, and so the variation of Px in that range is not that important. So making that assumption, we can simply estimate that the probability of getting an x in that range between a and a plus h is equal to the integration of estimation, so the p hat of x, which is the fact that in that range density is constant. Integrate this from a to a plus h. And this is more or less equivalent, as given that we are making an assumption that it is constant. This is equivalent to say, okay, we are looking, in fact, you know, we have this thing, we say, we have this, we are estimating this by a constant, and then we can just say that our estimation in that range is a rectangle. So that rectangle has a, so this is 0. So the height is p hat, and the width is a plus h minus a. So basically it's a width and p hat 8. That gave us a way to estimate that probability, assuming that it is constant and assuming, in fact, to be right, given that we see that this is equivalent to that. So it's more to say something like we have that interval and we are using the point here at a as, wait. So we have that point here and we are using that point here, which is p at a, as the estimate of the value. So of course we are off by this thing, but we are making this simplification to get everything more simple. So this is, in fact, it is here. So we have here our value that is used over that range from a to a plus h. All right. So from that, we are able to state that our density estimated at point x, assuming that x is in that interval, correspond to 1 over h, because we are in fact using this equal to that, and that thing is in fact equal to that. So we are plugging in the probability, the big P hat here, and we are dividing by h, because in fact we are sending this on the other side. This gives us an estimation of the density. And so if we are making histogram estimation in 1D, we are in fact doing something like this by first dividing the input space into compartments that we call simply bins. So we have bins that we are building up from over that domain. So each bin is of wide by h and position with respect to the origin. So basically we can say that, okay, we are working here. This is the origin, we call x0, often can be simply 0. And we are splitting this into some bins of equal width. So we are several here. We have one bin, another, and so on. These are all our different bins. And as such, from a data set of endpoints, we can estimate the density for a given x by counting the number of samples from the data set that are in the bin X. So if we have some value X, we say, okay, we have this domain here. And so, and then we have a X that is here. We are looking at the number of samples in that bin divided by the total number of samples, which is n, divided also by the width h of our bins. This gives us the estimation that we need. The choice of the origin x0 may slightly affect the estimator in the sense that we are moving the boundaries. So in some cases, moving a little the boundary may change the count because we'll get maybe a sample that will be assigned to another bin. And so in some cases, the bins maybe get one or few more samples than if we were positioned differently, but this is relatively light. The choice of the width H is significant, with really wide bins, we have much less bins. So the estimation in terms of counting the number of samples in that bin is much better. However, we've got a big part of the space that is approximated as a constant. So we have this with only few bins. So the precision in our estimation is much less. So conversely, if the value of H is low, we can get really many peaks because we will get many small bins, but with really few samples in each of these bins. And as such, the estimation or the value we evaluate may vary a lot. And if we are, for example, by chance having 2-3 samples in one bin, it may increase a lot the value predicted here. But this is just maybe a sampling artifact. And like I said before, if we have wide bins, so if the value of H is high, we have a much softer, a much better estimation, but it is much less accurate in terms of the value because the bins are really big, and we are approximating everything in that bin as one value. So an example here, what we see as the dashed red line is the real density. And what we see as the blue bars are the estimate from an histogram. So we can see here the estimate with an histogram is relatively accurate. It fits quite well the red curve. Let's get now an example where we are varying the width. So the first case here on the top, we have a H of 20. So it means that we have like 2 bins in here for 20 samples. So it is relatively, it is too coarse. What we see here is not that meaningful. If we go with a smaller width, we get that thing here, which seems to be more precise. And even here, we have something even more finer on the bottom right. And this is maybe too fine because we have this kind of artifacts here, which are not that meaningful, but because we have only 20 samples, when we have quite small bins, getting one sample outside would have an effect on the estimation. And we see in that same histogram, the real distribution, which is the dash red curve. So here, probably it's too fine. There on the top left, it is too coarse. In between, we have different trade-offs. So it's up to what we want to do to evaluate what is the best one. But I would say, as general trend, I would prefer that one, the H equal to 10, because we can see that we have a peak here that corresponds well to what we have in the red curve. Another thing here that is also corresponding quite well. So, and we are smoothing off that region here, which is not useful. Here, the bins are wide enough for not being affected that much with these samples. Histogram estimation in many dimensions can be done also. It's the same principle, but the bins here are corresponding to hypervolume. And so we have bins with equal upper volumes, so less hypercubes. However, such way to estimate density is highly impacted by the dimensionality, and it suffers a lot from that because we need to get a relatively good sampling density, in the sense that we need to get, in general, many samples in every bin, and given that we are increasing the dimensionality, we know that the sampling density is decreasing exponentially. So quickly with in 2D it's manageable, but in 3D okay, but we need more samples. More than 3D doesn't really make sense. And the performance will be relatively bad unless we have really large data set. A general condition for estimating, for an estimate to converge to true probability density is to say that the p hat is equivalent to the real p with large enough data set. But there are more than this. So we could say here that we say that the volume need to be reduced. So we should aim at getting as small bins as possible. So the volume of each bin needs to tend towards 0 as we have more and more samples. With a lot of samples, the number of observations per bin should be very high. So even though the bins are really small, we should have many samples in every bin. So at the limit, we should get an infinite number of samples per bin to be able to get good estimate. And the ratio of the number of observations per bin to the total number of observations should be high. So we should get less samples in each bin than the overall number of samples that we have in our data set. So these are limit conditions, but these are the general conditions where we can assume, we can consider that the estimation will be a good estimation from the, will tend to be equal to the real density. As example, here we have a 2D multivariate normal distribution that we see on the left. So this one is kind of skewed in that direction. So we have a non-zero value out of the diagonal, and we can see that the slope here of the covariance matrix is positive. So the correlation should be positive. And it is centered here around 2, 2. So this is the center. So and now the small dots that we see here are samples. So these are samples coming from that distribution. And when we do a 2D histogram estimation of the distribution, we get something like what we have on the right. We see here that each pixel is basically a bin in 2D, and the intensity of that pixel gave us the value in as estimation as p hat x that we've got. And this is corresponding quite well to the normal density, the distribution on the left, although we can see that there are variations, artifacts, and the pixels are relatively big. So even with such 2D estimation, we can see that we get some artifacts in terms of the size of the bin. And even with these artifacts, we see that the color is changing a lot. That means that the estimation may vary a lot from like neighbor pixels. One improvement over histogram that we can do is to make use of what we call naive histogram estimator, also known as Pearson window. So this consists to estimate the density around a given x as an hypercube of width 2h. So we are no more fixing the bins in the space. We are in fact estimating the density according to a given x. So we have an x and we are looking at its neighbors in the 2h bin, so plus and minus h range around it. So in 1D, the formulation is given here. We are estimating the density for at a given x as the count. So here we are counting the number of points in our data set, which are within the x minus h and x plus h range. So we are looking at the plus and minus h range around the the x that we care, and we are counting the number of samples in our data set that are located there. And we are dividing this by 2nh because we have a bin, in fact, center on the x that has a width of 2h, and we also have big N samples here as the total number of samples that we have in our data set. This is also formulated as this equation here. So this is exactly the same, but with a more formal notation, mathematical formulation. So we have the same thing as denominator that we have here, but we are summing somehow from data 1 to data n that we have in our sample set. And we are computing the W function over x minus xt divided by h. And what we are looking with that W function is in fact a function that is looking is the value in between the range -1 and +1. So basically it looks at is the value u here in between -1 and +1. If so, we are returning 1. Otherwise, we are returning 0. And as such, it is kind of counting the number of values between -1 and +1 in what we are giving it. But in the formulation here, we are using the x here to kind of adjust it around, to center around the x. And we are looking at dividing by h. So this is basically getting us to the range of center at x plus or minus h. So one of the good things with that is that we are removing the allogeneic zero. We are no more relying, so the boundaries are no more arbitrary, and if we have a point we close the boundary, the estimate can be more or less right. So we are removing this. However, the estimation is not continuous. It still has steps, but it has much more steps. So it is much more smoother somehow than the histogram estimation, but still it is with the small steps going on. Applied on the same data set than before with the histogram with still 20 samples, we have such result here. So we divided the h by 2 because it is in fact 2h as a range. So to be equivalent here, it is equivalent to what we have before with h equal to 20 with histogram. So we see here relatively smooth, but maybe here the h is too high because the variation is kind of really too slow, too smooth. We see on the bottom right the estimation with h is equal to 1. So here probably the h is too small again, and we see the real distribution with the dash red line. A good trade-off seems to be, to me, at h equal to 5 again. But we see that it is much smoother than before because we have this kind of shape that is going on a little up and then going up again. So this is relatively coherent with the real distribution. And we can see that even though there are steps, the variation are relatively smooth. And in fact, the kind of slope here that we have are, I would say, kind of nice in extrapolation that the scikit-learn is making with it.